How's it going, everybody? Welcome back. This is my first video in a series I plan to make on backtracking algorithms and just using recursion to come up with programming solutions. In this video, I'm going to be going over some code of a backtracking algorithm that I created for Uno. So the problem is, given a random set of cards in your hand and a top card to play off of, if there's a way that you can place all of your cards to abide by the rules of Uno and get rid of every card in your hand. So if we go over to Geeks for Geeks and just look at what they have to say about backtracking, they're going to tell you that there are three types of problems in backtracking. There's decision problems, and this is the first of the problem that we are going to cover in this series. This is what this video is on, and it's just given an input, can we get a solution to it? So we're looking for a yes or no answer. So with the Uno algorithm that I'll be showing you guys, we are just going to have an output of yes or no if it's possible for us to get rid of all of our cards. Next, there's an optimization problem, and it's just searching for the best solution. And lastly is enumeration, which is any solution that you find, you're going to add it to just an overall set of solutions. So if we go and look at their pseudocode for finding whether a solution exists or not, again, that's a decision problem. We're going to look at the code, and since we're using recursion, they're going to use some sort of base case or an exit condition to get out of this function. It's like if we found a solution, we're going to display it and return true to exit out of this function. But this is the main logic that you are going to have to set up your recursive algorithms using. So I'm going to briefly touch over the logic of it, and then we will look at the code and continue to refer back to this. So in terms of this Uno algorithm that we're going to be looking at, for all of the value, we're going to loop over all of the values, and the values are going to be cards. So for all of the cards that we have in our hand, we are going to only run this code where we can only do things with the cards that are valid. You see this is valid conditional, and in our example, it's a very broad function, but in our example, a card will be valid if it's the same number as the top card, if it's the same color as the top card, or if we're placing, say, a wild card, because then it doesn't matter the color, it's a valid card to place. Then you're going to apply your value to your solution and recursively see if the value that you just applied can lead to a solution, and if it does, you'll return true. No matter what you do, this is sort of the confusing part that's hard for people to wrap their head around when it comes to backtracking, is after you apply your value and run your recursive statement on it, you are going to remove it from the change that you just made. In context to the Uno, we're going to be placing the card and then seeing if a solution can stem from that. After we've recursively checked that, we're going to unplace our card and put it back into our hand, and then we're going to continue looping. And essentially, if this function can loop through and find a solution, then this will end up returning true and exiting out of the find solution function. And if you make it all the way down to the bottom without being able to find a solution, then no solution exists. So now we're going to go ahead and look at the code. I have written the code beforehand, and I have programmed some classes for Uno. Just to make it more organized, I want to say that the code will be available in the description of this video so that you don't have to reprogram the rules of Uno if you're not interested. You can also use it as a starting point and add to it, but the code will be available. So first of all, when we're looking through this code, we are going to first look at, I created two classes for this. I created a card class and then a deck class that holds the cards. So first we can look at the cards, and I will also refer back to this to bring some more context to it when we're looking through the code. So there's a class card, and it's initialized with a color, number, and special. Most cards have a color and a number, or at least a color. Examples would be like a red 5, a blue reverse, a green skip, etc. So color would match with color. In this sense, number would match with number. With this card that we're looking at now, blue would match with color, reverse would match with special. There'd be no number for a blue reverse. Same with green skip. And then some cards, such as a wild card or a draw 4 wild card, will not have a color or a number because wild cards do not have numbers. The second function right here is just a way to output the card class. It's not really important to the overall algorithm. It just helps you if you want to print out a card to see what it looks like. This is a way to format that print so you're not printing a class object. These next two functions are going to be helper methods. They are going to help verify our is valid. How do we check if a card is valid again? It's the card that we need to play off of, if it's the same number, the same color, or if it is a wild card. So this function will see if the number, if our card matches, so the card is itself, and then we're passing in another card to it. If it's the same color, we're going to return true, else we're going to return false. And the same logic, except we're checking numbers. So our is valid, I believe is what they called it. I'm going to double check again. Yes, our is valid is going to be is compatible in this sense. So just like I said before, if a card is compatible, it either has the same color, the same number, or one of the cards is a wild card. So this function is just checking that either of those three are true, and if none of them are, then it's false and it's not a valid card. So then we can look into the deck. At the top, if you need a refresher on the rules of Uno, and then this is just the card. Again, card is a color, number, and special. But if you need a refresher on the rules or the deck contents of Uno, this will refresh you. So an Uno deck has 108 cards. This includes 8 skip cards, 8 reverse cards, and 8 draw 2 cards. It's 8 because there are 4 per color, or 2 per color, and there's 4 different colors. There's 4 wild cards, and there's 4 draw 4 wild cards. And lastly, each color contains 19 cards, 1 number 0, and then 2 sets of cards numbered 1 through 9. So if we had a red deck, there'd be a 0, and then there'd be 2 1s, 2 2s, 2 3s, and so on and so forth. So our deck class is just a list of cards. So when we initialize it, self.cards is just going to hold, it's a list that holds all of the cards from this. It's going to hold this class of cards and just every card that we just went over. And then we're going to build the cards, or build the deck in the initialization. So if we go to the build statement, this is just looping through every single color in our deck, adding 2 reverse, 2 draw 2s, and 2 skips for it. Then we're adding 0 through 9 for each color, and our wilds and +4 wilds, and then we are going to shuffle. Next is just a helper method. I called it show. This utilizes the print. The print function allows us to print every single card in the deck utilizing this function that I was telling you guys about earlier. So without this, you wouldn't be able to print cards neatly. So our show method just prints every card and the length of the list of cards or the number of cards in the deck. Drawing a card is simple. If you had a stack of cards and you want to draw one, you're going to remove a card. So we're going to remove a card from our list of cards in our deck. And draw top card is very similar. This will draw the initial card that you play off of. So if you're playing Uno with friends, you're going to draw a number of cards, say 7, and then after everyone has 7 cards, you're going to flip one card over, and that's the starting card to play off of. So when you flip that card though, you cannot play off of any sort of special card. You just need any arbitrary colored and numbered card to play off of. So this is just going to try to draw a card, make sure that it's not a wild card or reverse or something of that sort. If it is, we're going to put it back in the list, shuffle the list, and then try again. If we get a card that's just a normal card, we're just going to return that card. So that's it for the Uno rules and logic of the game. Like I said before, this code will be down below in the description. So now we can get to the backtracking algorithm itself. So we'll start out with the main function. What I'm doing is I'm initializing a card of decks right here. And then I'm creating a player deck and a discard deck. The player deck is going to hold all of the cards of the user that we need to get rid of, and the discard deck is going to contain everything. It'll contain the starting card that we flip upside down to play off of, and then every card placed on top of that. This loop, what it's doing is just drawing cards into the player's hand. You can think about it as each player getting their set of cards, and then after that's taken place, then in the discard deck we're going to place the top card, and that'll be the card we have to play off of. So I can actually, I'll comment some of this out and just show you what this looks like now. So like I said before, we're drawing cards into the player deck. This is the deck that we are going to be running a recursive backtracking algorithm on to try to get rid of all of them, given the first card in the discard deck. If we do this correctly, the player deck will be completely empty, if it's possible. So I will go ahead and run this, and as you can see, each player got drawn a set of cards. I set it to 5, you can set it to whatever you want. And then the top card that we need to play off of is green. So going back to the code again, I'm going to go ahead and uncomment this. This is where we do this is where we call our backtracking algorithm. So I'm going to refer again to the Geeks for Geeks logic, because I think they do a really good job of showing some pseudocode. So like I said before, we're going to have some sort of base condition to get out of our recursive algorithm, and we're going to loop through all of our values, find our valid moves that we can take, apply it, recursively check if our new applied value will lead us to a solution, and then we're going to remove it after we recursively check. So if I go to our find solution, this is our base condition, and our base condition, like I said before, is how you get out of the algorithm. So we have to think about, what does it mean to be completed? We're given a set of cards in our player deck and we want to get rid of all of them. Well, if our player deck is empty, or if the length is equal to 0, then we have found a solution, assuming we have correctly followed the rules. So this is how we will get out of the recursive function if we find a solution. There'll also be a way to get out at the bottom. So next we are just going to hold a variable for top card, and top card is the last card on the deck of our discard deck. So -1 is the index to get the last value. So if we had like card 1, card 2, -1 would pull card 2 from that list because that's the most recently added. So I went about this a little bit differently. You can think about it as pre-processing, or I don't know. I think that this is an easier way to understand it. Is you can build your list beforehand. So what I'm doing is I'm looping through every single card in the player hand, and I'm checking if that card is compatible with the card that I need to play it off of, and if it is, I'm going to add it to a list of playable cards. So going to our backtracking solution, instead of looping through every card and then checking if a card is valid and applying it, I'm just looping through a card and checking the value, and then I'm looping through the list of cards that we already know can be played off of. So it's the same overall logic. I'm just creating a smaller subset of valid moves to do. So we only have to loop through the valid cards. So then this is where the beginning of the backtracking algorithm is going to work. I'm going to loop through all of the cards and the playable cards. These are all cards that we know are able to be played. We're going to remove the card from the player deck and place the card into the discard deck. You can think about this as physically playing the card. We're removing the card from our list of cards and we're adding it to the list of discarded cards. So in theory, or just the way it will work actually, is once we play this card on the discard deck, this will be the next top card in the next iteration of this loop, or the next recursive call of this loop. And then this is all the recursive step is. We're going to now call the recursive function. We're going to say, can we find a solution with this change that we just made? So we made the change right here. We've applied the value. And now we're going to say, with the value that we've applied, figure out if there's a solution. And then after that, still in this for loop, we want to then revert the changes that we just made. So we're going to add the card back to our player deck and remove it from the discard pile. So we're doing the complete opposite of these two lines. We are undoing the work that we just did. That way, we can check recursively for each change. So we can go through a card, place it, and say, hey, with this placement, can I find something? And then we undo it, and then we go to the next card and place it. Hey, with this card, can I find something? So that's all that's doing. And then you'll get down to the very bottom, and if you've made it this far, and you're out of all of your playable cards that you can play, all of the valid moves, and you've gotten down to here, and your recursive function hasn't found a solution, and it would find a solution by being able to place all of your cards and then the length of your deck being 0, then we know that we could not find a solution for this, and we're going to go ahead and return false. So I can refer again to the backtracking introduction. So we have created our base condition. If our player hand is 0, our player deck is 0, we're going to return true, and then we're going to loop through our valid moves, apply the value, check if with this applied value, if we can keep repeating these steps to come to a solution where we have an empty player hand, meaning we've successfully placed every card, and we're going to remove it after that check so that we can continue checking each other card. If we make it to the bottom, we return false. So we've almost completely turned that pseudocode into code, and now I can go ahead and run it. With something like Uno, having a smaller hand, it's going to be more difficult to be able to place every single one of your cards. I'm hoping in a couple of attempts I can get this to be a success, and then we can kind of step through the cards and see of how it maybe came to a solution. I want to remind you that this is a decision backtracking solution, meaning we are simply saying yes or no if we have been able to find a solution. So going back to the 3 different types, this is a decision. We are going to figure out if we can find a solution. So stepping through the main again, creating a deck of cards, assigning some to the player, assigning a top card to the discard deck, and then we are going to, just for outputting sake, we're going to show the cards that the player has and the card they have to play off against, and then all we simply do is call our find solution with our player deck and our discard deck. So the inputs to this is the player deck and the discard deck. I apologize, I should have touched on that earlier. But if we are able to find a solution, that means that we have recursively gone through, and for each move we've been able to find a move to where we can empty out all of our cards. If not, then we simply cannot do it. And yeah, that's that. So I'm going to go ahead now and run it again. And this says we cannot place all of our cards. I will run it again. We can place all of our cards. So this one worked. This first execution didn't. This one does. So we can step through it real quick. So these are the cards that we were given. And our first card was to play off of a blue 6. So different things that we can do. Hopefully, yes. Okay, so this is a good example as well because it shows that there are multiple ways to do it. So this can later be turned into an enumeration problem to find all of the best or all of the possible solutions. We just know that a solution is possible, but we can end up creating a list or a set of all possible solutions. So if we look, our top card was a blue 6. So just from the top, we could do a blue draw 2. We can do a blue number 1, and then we can do a blue 8 followed by a yellow 8 followed by a yellow 6. So that's one possible solution. Now you might be able to tell that there is another way to solve this. We could use, going off of our blue 6, we can match the number and do a yellow 6. And then we can match colors and do a yellow number 8. And then go back to blue, matching the numbers, a blue 8, a blue 1, a blue draw 2. And also in that solution, instead of going from a blue 8 to a blue 1 to a blue draw 2, we could have went from this 8 to this draw 2 to this one. So there are multiple solutions to this problem. So in a later video, I'm thinking about showing how to do enumeration problems, but this is the general idea of backtracking, is going through a list of potential moves that are valid for your program, and then you are going to apply some sort of change. Then you're going to recursively call your solution algorithm with your inputs again with the changes that you made to see if you can continue doing that to hit your exit or your base condition. But then after, the most important part is remembering that after you make your change in the same loop, you want to then remove the changes that we just made so that we can try other cards in this loop as well. I thought I should add that when we find a solution, Maybe you guys want to see the order that your computer and your algorithm solved it. So given that we have a list and we pass it into the function, we are going to be able to see our discard deck afterwards. So we can write a for loop. We can say like for card and discard deck print card. So that is a possibility. That's something that you guys might be interested in seeing. This will give you a solution that your backtracking algorithm solved. Given some sort of constraints may be necessary, it might not be the most optimal for what you're trying to achieve, and this will only give you the first solution that solved the algorithm. This will not do enumerations. It's the algorithm was not set up. Again, if you guys are interested in seeing potentially an enumeration version of this, I can show you guys that. But making that change and running it again, you can see that we could place all of our cards. We started with a blue 6, so that was the first number in our deck, and then our algorithm did blue 1, a wild, and then some greens. So that's the solution. And then maybe just for fun, I should show you guys it on a bigger deck. Usually the bigger your hand, the easier it is for your program to find a solution, since there's more colors and numbers in the mix. So I think that it should have no problem coming up with a solution for something like this. So these are the cards that our algorithm was given, and this is the top card to play off of, and our algorithm was able to find a solution, and we can just kind of walk down this list real quick. So we went from a blue 1, that was our top card, to a wild, and then we used reds, and then we connected our 3s to jump to yellow, and then we connected our 5s to jump back to green, and then we used a wild card, and then we went to blue and used our blue to jump back to red, and then continued down, and we were able to discard every card in our deck. So I thought you guys might want to see that. You know, it's more fun to see it that way, and that way you can check that your solution is correct if you were interested in that. I think most people would be. But yeah, with that note, have a great day or night. Thanks for stopping by.